Okay, I think that's working. So, all right. I guess what we should probably do is take a quick look, as I usually like to do, at where we're at in the course. We're actually about a week behind, which isn't too bad given all the issues we've had. Um, we'll be doing process synchronization this week, which is normally done last week. So, as I said, we're about a week out, roughly. Um, I'm also not sure entirely how great the reception is going to be here. I'm at the Ronald McDonald House in Rochester, and I'll be here at least through the weekend. I'm not sure about Monday yet. Keep posting on email. It's possible Monday will be the same, but it's also possible I'll be home by Saturday or Sunday. So we'll let you know. All right, so operating systems. I'm going to get some grading in this weekend too, so that'll help with things. This is week 11, and I launched all this content here. Chapter 5, some semaphore code examples. They're labeled as week 10, but actually that's week 11. Some extra slides for deadlock and dining philosophers. Some stuff about signaling and semaphores. There's a mutex lab, which I don't think you're going to be ready for yet today, quite honestly. So we'll put this off, but we'll at least have to do this by Monday. And it goes through and walks through a bunch of stuff. We might get a chance to talk about this today, but as far as the lab goes, I'm not going to worry about having a lab due for this Friday like we normally would. Now the semaphore lab, you can download it here. I'm just going to put a note quick before I forget that is. So we'll get to that on week 12, probably Monday. All right, so back to slides. Process synchronization. So now what we saw last week that we were looking at this content, there can be a great many issues with threads because they can stomp on each other in shared memory, which is something I've been intimately familiar with lately in a project I'm working at Institute with shared memory. And so this is a very real world thing where you've got two threads, processes, whatever they are, and they need to synchronize their data between the two different processes. So the main objective right now in these slides is to talk about why it's important, what the critical section is, and what tools we have at our disposal to ensure that essentially only one thing is in the critical section at any given time. So processes can be executing concurrently. Obviously, that's the big premise behind all of this, is that you can have multiple processes, multiple threads running concurrently. And because of that, you do sometimes get yourself into issues with that. Sharing memory. What if you write to some memory and something else was already assuming that it was placed in that position? Or worse yet, you wrote to that memory and something else assumed that it had already been read and therefore got the old value of it. They have an example here. So suppose that we wanted to provide a solution to the consumer producer problem that we talked about from class a few times ago. Remember, producer consumer problem was that one where basically the producer is making a whole bunch of resources. Consumer, as resources are created, takes those resources and consumes them. So if we want to fill all the available buffers, we could actually just have a counter that keeps track of those fills, incremented by the producer and then decremented by the consumer. But the reason this becomes an issue with synchronization is it all becomes, well, when are you actually updating that counter? So taking a look at that in some more detail, because before we basically ignored the problem, but now we're basically saying, okay, so here's a while true loop for producer, and this basically says, okay, if we're currently at the maximum buffer size, we'll do nothing because we can't create anymore. That's the maximum amount that we're able to create. Otherwise, we produce that item, which is called next produced, and the buffer at whatever the in position is can be set to the thing that you've produced. And then since this is sort of a wraparound buffer approach, we take in plus 1 modulus the buffer size and add 1 to the count. So that's essentially just filling the buffer, and no really worries yet about synchronization, which we'll talk about in a little bit. Now the consumer, meanwhile, is basically saying if there's nothing in it, and again that counter is going to be shared memory just like the buffer is, then we're not going to get anything out because there's essentially nothing to be gotten out of the buffer. Otherwise, we take the current position of out and put that next item in, that as next consumed is our variable name. So here's where we get into a problem. Counter plus plus could be implemented in a bunch of different ways. Going back to assembly, if you did have that course, you could essentially, what you'll remember from that course is that everything revolves around registers. So essentially we have to populate a register in order to add to a register, and memory variables need to be manipulated through registers. So we get, for example, the contents of the memory location counter stored in register 1, increment register 1, and then store that back to memory. That part right here is all assuming you understand that this is basically what's happening at the assembly level. So if you haven't had assembly class, this is a 400 level course, so the theory is that for the most part you will have had, the new theory for the new curriculum is that you'll have had most of your 200s before you take your 300s and most of your 300s before you take your 400s. So most of you should have had that, but if you haven't, just kind of filling you in here, it's a lower level than the high level languages like C and C++ and Java, that breaks things up into the actual registers that are stored on the CPU itself. So when we say register 1 equals counter, we're pulling from a memory position there and sticking it in a register. Now likewise, we could easily take that same logic and apply it to we could take that same logic and apply it to counter minus minus. So register 2 gets counter 2, register 2 subtracts 1 from itself, and then counter 2 gets put, whatever value that turns out to be, gets put into the memory location. So now that we've broken this up into assembly, it's probably a little bit more obvious Why? This can cause race conditions, because let's assume that this is the sequence of execution, and these are interwoven processes that are occurring, one being the producer, one being the consumer. Sequence 0 might be that the producer executes register 1 equals counter. Then maybe sequence 1 continues and says register 1 equals register 1 plus 1. But now comes along, in this sequence diagram, comes along S2. S2 executes register 2 equals counter. But counter, as you could tell from the fact the producer didn't get to finish its sequence of 3, counter hasn't been updated yet. It's still the old value. And so now register 2 says register 2 equals register 2 minus 1. But if you were looking at this from a higher level, you might have assumed that, well, if counter plus plus happened first, then we should be fine, because when the consumer comes along, counter plus plus already happened, so therefore the variables are properly updated. But they're not, because assembly, essentially. They're not updated properly because this is a race condition. We have no really way of knowing, once we schedule these two things off on separate processes or separate threads or separate processes that themselves have separate threads, it's very hard to know. And we'll talk about scheduling later. That's like chapter 7, I think. We'll talk about, well, how do you know when to schedule these various processes? But for now, it's a black box. We just send it off to the OS and it does its thing. So here's where the problem is, because now, as you can see, backing up a step here, register 1 equals 5, register 1 equals 6 at S1. At S2, register 2 equals 5. Register 2 equals 4 because we subtract 1 to it. And then finally S4 comes along, which was supposed to come along earlier because that's part of that first sequence that got initiated of the counter plus plus, right? But finally that comes along and it says, okay, set the counter to 6, because register 1 was set to register 1 plus 1. But meanwhile, we have to go back to S5, which is that last sequence of events in the counter minus minus, and we say counter equals register 2. However, since we got the previous value of counter, not the current value of counter that would have been updated by the counter plus plus, we got the previous value of it. We therefore pulled off 5, subtracted 1 from it, and now we're at 4. So we've got a value discrepancy here. We said counter plus plus, so we should go up to 6, then we should go up to counter minus minus, so we should go down to 5. But as you can see here by this chain of events, we're actually at 4. So in computer science, this is a classic case of a race condition. We're updating a value midstream and reading from a value midstream, therefore creating this race condition about who gets to that variable first. That's essentially why they call it a race condition, is it all comes down to who gets to this first. In a certain sequence of events, this code would be fine. If you did the first 3 lines here as your S0, S1, and S2, then everything's fine. Who cares? There's no semaphores needed, no mutex needed, no whatever, the stuff that we're going to talk about soon to prevent this. None of that is actually needed. You're good to go. But a race condition basically says it's all bets are off and it's whoever gets to that first, and it could cause problems. So this is one thing we refer to as the critical section. So critical section was essentially this idea that came about that said, well, in order to prevent this, if you look back at our old race condition that we just went over, this is essentially the critical section here, right? Like, ideally, if you get into this section you don't want things going amok. You don't want to have other things interrupting those processes. Oh, and by the way, I should say too, if you have any questions, you can use your mic or you can use chat and just shout out at any time, just like we were in a standard classroom. Anyway, the critical section, basically, intuitively, what is layman terms is just the code that we don't want other people to mess with. So in this case, we don't want other people to mess with these 3 lines. If things happen to these variables that are in these 3 lines outside of this system, then all bets are off. So if register 1 or counter, and in this case counter is the big one, if that gets modified by someone else while this critical section is executing, we're going to be in trouble. Now, once we're done executing that critical section, then we can do whatever we want, because it's kind of like a lock. Like, think of it that way. You've basically said, I'm going to have a lock, and that's, well, I'm getting ahead of myself, but you're basically saying, I don't want anyone else to be messing with this while I have it checked out. It's like checking out a book from the library. You check it out, you have it, you don't want someone else midstream in the midst of you checking it out to be able to grab it or something. You check it out, you have it, no one else can get it until you actually bring it back. It's not like someone can just sort of like, come to your house one day and say, hey, I need to look at that book for 10 minutes. Without semaphores, that's essentially what you're allowing, your code to do. You're basically allowing it to muck about with things that it shouldn't have permissions to mess with. And so that's that's what the critical section is. So anytime we're updating common variables or tables or writing to files that are shared, there you might have critical section problems. And what you have to ask yourself is, well, what is the critical section? And the critical section is going to depend on your implementation. It's going to depend on what variables you've picked out and how those variables are being updated. Frankly, sometimes even what the assembly looks like at the bottom of the stack there. So some continued critical section. This is the general structure of any given process. Now that we've introduced this concept of a critical section, you can think of your process as basically doing a couple things. It sets up the ability to have a critical section, but to do that, you get this thing we call the entry section. It sets up for the critical section. Critical section is done. We get to exit section, and then we get to the remainder of the process. And this is just sort of in another way of explaining it. Well, turn equals J. Do your critical section. So basically, if if J represents you, you go in and you do your you go. So if J was set, then we can do our critical section. And then we can do our remainder section after. I'm pausing a little bit here because I always like to be honest when I see some glitches here in these kind of things. And one glitch I'm seeing, well, what I mean by glitch is a possible source of misunderstanding. When we say turn equals J, you're really saying, is it my turn yet? And if it is my turn, I'm going to go to that critical section. So turn equals J, that's basically saying pick a next turn. Okay, so the critical section is going to be shared. Notice how it says algorithm for process PI. So that could be P0, it could be P1, it could be P2. They all share the same pseudocode. Okay, so that's the first thing you have to understand in deciphering the pseudocode. The next thing you have to understand is that basically we're saying while you know, while my turn is equal to whatever J was just picked, then go into the critical section. And then choose a new turn. And that's essentially, this is what that does. And it's not very clear, I don't think, in this slide. Choose a new turn for someone to have. And that's going to be, in reality, when you do this in implementation, that's going to be actually a function call. But this is just pseudocode, so that's why I think I want to spend a little more time on it to make that clear. So, all right, on to the solutions. And they've been kind of implied a little bit in the previous slides, but what you can do is you can essentially solve this in a variety of ways. You can have mutual exclusion, which we just talked about essentially. That's where if process PI is executing its critical section, no others can be in their critical sections. Otherwise, you can have progress monitoring. So if no process is executing its critical section and some process wishes to enter its critical section, then we schedule and allow entry into the critical sections that are waiting for that access. And then we've also bounded wait, which is basically similar to mutual exclusion, although it basically says you're only allowed to get into your critical section a certain number of times. Now, critical section handling in an operating system level, we'll talk about this in the coming slides, but basically this says that we can either be preemptive, which means whatever process is running, we can boot it, essentially. And then non-preemptive, which is like blocking wait style, where it just runs and nothing else can get into it. So nothing else can interrupt the critical section in that case. And OSs have different ways of solving that. I'm going to skip Peterson's solution for now. Okay, so taking that algorithm, that pseudocode, into a little bit more depth. Actually, let's go back to Peterson's solution because that's going to wrap into the slide. So we can do a two-process solution. And this all assumes, because at the root of it is the load and store for memory. So we can assume that that's atomic and it can't be interrupted, which is a fine assumption to make because, sorry, my son is in, yeah, not important. So we can load and store machine. These load and stores are the lowest level. This is assembly level code. These usually cannot be interrupted, although there are cases where it can, but that would be a rarity in the sort of computer organization architecture world. Now we're also going to assume that, okay, we've got two processes sharing some global memory, which is going to be like a turn integer and a flag that's set. Turn, as I said, that's going to be computed, and it's going to basically tell us whose turn it is to enter the critical section. Flag basically says, okay, I'm ready to enter the critical section. And the process itself will set flag, and that means, okay, I am ready to go into my critical section. So it's the prep work, basically. Setting that flag I to true basically says, I am ready to go into the ith, I am process I, and I am ready to go into my critical section. Again, turn equals J just gets the turn. And so then we say, while flag of J and turn, then do the critical section for that particular process. So you should be able to see that this means that the three requirements are met. We've got mutual exclusion preserved. PI is going to, the process that's labeled as I is going to enter our critical section only if either the flag at J is false or it's our turn. So basically, progress requirement is satisfied, and so is bounded waiting, because we can just set as many to be waiting as we want. From a hardware level, we see that there's a lot of systems that provide hardware support for locking of critical section code. And basically, this is hardware level locking that is called from the software to basically lock that synchronization code. These locks eventually percolate themselves up to the software, and you just basically say acquire lock, then do your critical section, then release lock. It handles the rest for you. I mean, there is a lot, obviously, in Linux coding. There is a lot of extra work you have to do to get like the lock ID and some of this other stuff. But you can basically say, I'm going to get a lock as this process. I'm going to get a lock on that memory. Then I'm going to do the critical section. Then I'm going to release that dot lock and do the rest of what I have to do. So test and set basically just says, okay, return whatever value is there, and set. This is a standard design pattern, and actually, I think I'm going to skip that because it's better suited for a software engineering course. I usually skip down to mutex locks at this point because, as I said, there's 80 slides here, and can't possibly cover all of it, but mutex locks are something I definitely want you to be aware of. The hardware lock solution is a tricky matter because there's a lot of things you need to know about the hardware and a lot of calls you need to make. Instead, what the OS has done is essentially implemented its own lock called a mutex lock, and it operates in a very similar fashion. It acquires a lock and it releases a lock. So acquires a lock, does the critical section, releases the lock. A sec, I'm gonna grab my bottle of water. It's right over here. Hopefully that way I'm coughing a little less. So mutex is basically, in the design of it, it requires a busy wait. So we basically say acquire, and then while it's not available, it just keeps waiting until it's available, at which turn it acquires it and returns it, and then after it's done, it sets it as false. That's no longer available after it's done with its critical section. So mutexes and semaphores, those are the big things we're going to be working on this unit and actually into Monday as well. Semaphore allows you to have a slightly more sophisticated way of synchronizing your variables. Semaphore basically is an integer style variable. It's an integer type, and it allows you to either do the P or the V, which is basically either a wait or a signal. So we can wait on a certain signal, which basically inside of the wait, all that does is a busy wait. And then we can do a signal, which is S++. So you see here that wait S basically says, well, S less than or equal to 0, busy wait. And S minus minus. So when you call wait once and say there's nothing else that's called it and it's at 0, it'll go down to -1. Then someone else can signal that, right? So someone else can say, okay, I'm done with that. Signal it, increment S. So S goes from 0 to 1. And then it goes back to, or I mean, -1 to 0. And therefore it can finish its waiting. So the way this works is we've got binary semaphores and counting semaphores. So let's say process 1 and process 2 require, or I'm sorry, the wait 1 and wait 2, which is basically what P1, P2 are, require that signal 1 should happen before signal 2. So this solves our synchronization problems. Why? Well, because we can then say this section of code has to happen before this section. So this is what we call a semaphore sync behavior. So basically, hello? It's lagging out pretty bad. So anyway, we can create a semaphore sync, initialize it to 0. And then basically just signal, so process 1 comes in. And let's say that the sequence S1 has to happen before S2 happens. Note that process 1 has S1. Process 2 has S2. So this can solve our race condition issue essentially, because we could say that, well, for example, you have to do count plus plus before you do count minus minus or something like that, like we saw in that earlier example. So we could set a semaphore up that basically is operating on a signal wait basis. So process 1 does its stuff as sequence 1, which is fine. Sequence 1 is supposed to happen first, right? It doesn't have to wait for anything else to happen. Then it can signal back to say that it's done. Meanwhile, process 2 does a wait, which is a busy wait, for sync to happen. And then once it's done, we do S2 because we're going to assume that S1 was done, since that's how we define the semaphore to operate. So, what is going on here? My slides just suddenly went wonky. So semaphores in the OS end up having a waiting queue for them, which is going to have the value, which is the integer, and a pointer to that next record in the list. And then what can happen is we either place the process invoking operation on the appropriate waiting queue. That's what a block does. So block basically says, okay, I'm going to, this is being blocked, so I'm going to go on this waiting queue. Or wake up means that signal occurred, wait is done, therefore I'm going to wake up. So those are just internal details that the OS has to take care of. So what we can do is essentially implement this without busy waiting now, because we have our waiting queue. We know what's waiting, and therefore we can simply just do a block operation, which just places it on a queue. Now, of course, the OS has to handle that. It has to handle the fact that we're now in a waiting queue. And what being in a waiting queue does is quite similar to being in a busy wait situation. It essentially postpones that process for a period of time. So that's what semaphore is doing without busy waiting, is it's postponing that. Now, to implement this, here's two functions. We've got a wait for semaphore S, pointer S. We can update the value to minus minus because we know that we're doing a wait. And then we can add that to the list. Then we block, which basically says, don't do anything with that process until this wait is done. Now, this is a blocking situation, and I just got done telling you a week or two ago that the whole world is going asynchronous as opposed to synchronous. So you might be asking yourself, well, why are we where's the disconnect? Why are we talking about this? Why do people use these things? Well, it's a catch-22, because you see the word block there. What block really means is how do you handle situations where you've got multiple processes and multiple threads? You want to do things asynchronously as much as you possibly can. But no matter what, every once in a while, you're going to be using shared code, shared, data or files or whatever that cannot be run concurrently. So, what that means is, if you have a situation in which deadlocks could possibly occur, race conditions, or any shared memory situation, you're going to run into this. You're going to run into the need to have this kind of a locking scenario. I can guarantee you that if you haven't done threaded programming before, or process-oriented programming, this will come up. You're going to see other issues where you have to lock certain things. And semaphore is one way of doing that, and it's kind of a universal way at this point. So here you see, there's a big tangent, but hopefully it's helpful to understand the big picture here. The signal function knows that basically that value should be incremented because of the fact that when we do a wait, only if the value is less than 0 do we start doing our blocking. Otherwise, we continue on and we go right into the critical section. Now, this is interesting here, this bit, because, man, excuse me, wasn't this bad all day? So basically, if the value is less than or is equal to 0 at that point inside of the signal, we remove that process from the list and we assign a wake-up call to it. There's some other problems I mentioned. I did talk about race conditions, but deadlock is another big one. Let's think about what deadlock is. Well, I don't know if you've ever heard this term before in your CS studies, but basically this is a common situation where we've got two processes, threads that are running processes, processes running, processes that are running threads, what have you. It doesn't matter if threads are involved or not, but basically it's two distinct execution units, which is why we're calling it processes here. These can be waiting indefinitely for some event that's supposed to be caused by one of these processes that maybe will never happen. Here's an example of one. Let's say S and Q are semaphores, and we initialize them initially to 1. So process 0 waits on S, and it waits on Q. Process 1 waits on Q, and then waits on S. So it's a deadlock because we signal S. Well, first of all, whoever gets to S or Q first is going to get it. But right after that, that process got the semaphore, so therefore the other process isn't going to be getting it. So if we do a wait S in P0, that's fine. We do a wait Q, that's fine. But at the point at which we're then at sequence 2 at that point, because S0 would be wait S, S1 would be wait Q, S2, the third sequence, would be either wait Q or wait S. But they're not giving that stuff up yet, because as you see there, the signaling doesn't happen until after those waits are done. So that's what we refer to as a deadlock. Another popular topic in this area of CS is starvation, also known as indefinite blocking. This is where we get in a situation where the process is never removed from the queue. No one's ever signaled it. It's just starved for resources, basically. So, I'm going to try to move on at least another 10 minutes or so. Here's some classical problems of synchronization, and we'll be talking about these more as well on Monday. We'll probably try right now to talk about bonded buffer and reader-writer. These are classic computer science hallmarks, of like operating systems. Everyone talks about them, and they show some common problems in process synchronization. The first one, bounded buffer, basically says that we've got n buffers. Each of them is holding an item. We set the mutex to the value 1. We set another semaphore called full to the value 0. And we set a semaphore empty, initialized to the value n. So basically, empty is going to be however many buffers there are, is what that's going to represent. So the producer process can basically say, produce an item, then wait on empty. So remember, when we wait on empty, initially that's going to be fine, because we're, if you look again at our semaphore implementation, where was it? Here we go. If we wait on empty, well, empty is initially going to be set to however many buffers we have. So it might be like 8 or something. So it means it's going to do no busy waiting. And it's initially going to get right in there. So that's fine. Then we're going to do a wait on mutex. Mutex is initially set to 1, so that's fine. We add it to the buffer. We signal mutex because now we're out of our critical section. And then we signal that we are full. So we're signaling that something is there, basically. All right, so sounds good so far. Let's see where the problem comes in here. Now, what we're going to do in the consumer, however, is we're going to say wait on full. Okay, fine. Wait on mutex, and then remove an item from the buffer to the next produced. So this bounded buffer problem is a typical case of where you have to use these semaphores and mutexes in order to solve this. If you were to try this bounded buffer problem without these, you would see multiple problems. So we use the bounded buffer to sort of show how we can solve this type of, how we can essentially solve the producer-consumer problem. And per the producer-consumer problem that we saw before, if we use semaphores in this case, as we have, we essentially get around the problem of basically how do we can we read objects that haven't been fully produced already? Well, with these three semaphores, we can get around that. We basically say that, okay, the mutex is the thing that's the lock, and that's set to 1. So someone can get that at first, but only one person can get that first, and the other person is going to have to wait till that gets reset back to 1. And that's essentially the solution, because this wait mutex is surrounding, you'll notice it's surrounding the that wait mutex and signal mutex is surrounding the part at which we're messing around with the buffer. Here we've got wait mutex, signal mutex. Again, it's surrounding the part where we mess with the buffer. So we know that that's essentially solved this situation now, and you can we'll look at bounded buffer a little bit more later on. But now I wanted to get into reader writer. So reader writer is basically similar to a producer consumer problem. So here we've got a shared resource which can be used by multiple processes. Any number of readers can read from the shared resource, but only one writer can be writing to that shared resource. So the problem basically says, how do we allow for multiple readers to read at the same time, but only a single writer? And this happens a lot in various things, whether you're looking at saving of cloud data, even if you're looking at web services and things like that. I mean, you don't want people able to access your server data and be able to write to it just at any given time. You don't want multiples, because then you're opening up files for write simultaneously, and that could cause big issues. I guess what I'm thinking here is, if you think of in terms of things like Google Docs or other cloud-based services, they've got a real issue on their hands, because there you do have users modifying files seemingly simultaneously. The trick about it is the keyword there, seemingly. It's not really that they have write access for all those people at all times. Under the hood, what's really going on is that if someone does an update, say in their Google Docs file, and someone else does an update, well, there's going to be a critical section somewhere that basically says, okay, whoever gets to it first gets to do the write. The other person is waiting until that other person is no longer waiting. And it's going to be happening in a number of milliseconds that you're not going to notice. But it is still the reader's writer problem. So if you look at this stuff in a more modern lens, such as cloud computing or whatever you want to do, networking or something, still very valid. Because there's going to be plenty of times you want a bunch of readers, but you don't necessarily want more than a writer, more than one writer. So what you're going to do is you're going to basically have some shared data, which is your data set, an RW mutex, so our read-write mutex, set it to 1, and our mutex, our semaphore mutex, which is set to 1. Okay, so to solve this now, we say in the writer process, we wait on the RW. So RW is initially 1, so whoever gets it is in there first, and great, bang, we're done. Reader, a little bit more complex actually. We have to wait for that initial mutex, which we're going to get right away. But then all we're doing, the only thing critical about this is our read count. If the read count is 1, so you notice that the read count is initially set to 0. That means some new data has arrived. So we're going to have to wait on RW to write that data out. So we wait on the update, and then we update it. We do our reading. So here we're not, we got signal mutex in there. Now, multiple readers can be going in there, and we can say read count plus, whatever you want to do. But they're not going to get into their critical sections at the same time. So that's the critical part. Though the difference, though, is that the performing of the reading is actually not, in this case, that's not the critical section. The real critical section here is the updating of the read count for both of these. So that's kind of an interesting twist on that problem. And there's a few different variations of this you can sort of read up on, all of which study more complex examples of the reader-writer problem, which is a subset of the producer-consumer problem. So, all right, we're at about almost to slide 40. I think what we're going to do Monday is we're going to finish this out with Dining Philosophers, and then I'm going to show some examples in class to prepare you for the lab. And the lab probably will take us both Monday and Wednesday, but we'll see how far we could get with this stuff. I'm going to end now, especially since we had a fairly low attendance. I don't know if it was because of the technical difficulties at the start. This is the actual class time, at least it was for most of this recording. But it took a bit to get started here. I don't have headphones and stuff. So anyway, I'm going to stop recording unless people have... there were, I think we had as many as 3 people on at one point. We have 2 now. If either of you guys have questions, feel free to type them in or voice them. Okay, cool. Yeah, no problem. So we will be back in touch soon about what's going on for Monday. It might be this thing again. It might not be. Kind of one day at a time, but it's coming soon that I'll be back in GB and things will get back to normal. So, and hopefully for the best. Hopefully, no more of this stuff. So, we'll see how it goes. So thanks for tuning in, and I will be posting this on YouTube. Talk later.
Why will you be posting that on YouTube?
Because that's what I do.